So we were talking about the combustion, complete and incomplete. Okay. So in general, we should we give enough amount of air in order to avoid incomplete combustion, in order to provide the required provide first a good if you want a combustion that is not very harmful, that will not produce monoxide of carbon. Sometimes in especially in combustion engines where you have for cars, sometimes we use incomplete combustion to increase the efficiency, because if we provide in excess of combustibles, then we can ensure if you want a more production of energy, and in this way the efficiency of the car can be increased, but at the expense of the if you want the environmental effect. Okay. So if you will take a course on combustion engines, you will study, of course, complete and incomplete combustion, and to which, and of course, even if it's incomplete, we don't we use a certain coefficient of excess of air that is not very small, and minimum it will be 0.8. What I mean by this, we should provide more than 80% of the required air that is enough for combustion, because if we reduce a lot the amount of air provided, then we will have a lot of monoxide of carbon, which is very harmful to the environment. Okay, but here in our applications, in these applications, mainly we work with complete combustion. So the products are CO2 and H2O. Now, for the chemical reaction, how to write the chemical reaction? It's very simple. Okay, so first I know that I have that CH4 plus O2 will give me CO2 and H2O. Now, to know what are the coefficients, it's very simple. I apply the principle of conservation of mass. Okay, so here in this term I have one C, so I should have for the other term also one molecule of C. Okay, so if here I have CH4, I should have here one CO2. Now I move now to hydrogen. Okay, here I have in methane H4. So in one molecule of methane, I have four atoms of hydrogen. Okay, so I should have also 4 here, and since it's H2O, so to have 4H, it should be 2H2O. Now at the end, I determine the coefficient of oxygen. Why I kept oxygen for the end? Because I can find it here in 2 products, in CO2 and in H2O. So in total, for this combustion, I have in CO2 two molecules of oxygen, and in 2H2O I have 2. So already 2 plus 2, it's 4 oxygen. 4 oxygen is equivalent to 2 molecules of O2. Okay, so the coefficient of O2 will be 2. Now, once I determine the chemical reaction coefficients, I can find, for example, if I burn this amount, this mass of CH4, what will be the mass of CO2 released? Okay, how to do this? You can simply write the following. We can write from this equation here, okay, that 1 kilomole of CH4 requires 2 kilomoles of O2 in order to produce, will give me 1 kilomole of CO2 and plus 2 kilomole of H2O. Okay, now in order to know, if you want, what is the mass of CO2 produced, you need to know the molar mass of each component. Okay, how to find the molar mass? You have for CH4, you know that the molar mass of C is 12 and for H is 1. So if I have 1 kilomole of CH4, the molar mass will be, the corresponding mass will be 12 times 1 plus 4 times 1 for the hydrogen. So it's equal to 16 kilograms. Okay. So if I burn 1 kilomole of CH4, I am burning 16 kilograms of CH4. And to know how much kilogram of CO2 are produced, I say it will correspond to the production of 1 kilomole of CO2. And the mass of 1 kilomole of CO2 is corresponding to in 1 kilomole of CO2, I have 1 kilomole of C and 2 kilomole of oxygen. So it's equal to 12 plus 2 times 16, which is equal to 44. Okay. So what can we deduce here? For example, in this reaction, if I burn 16 kilogram of CH4, I am producing 44 kilogram of CO2, which is really a large amount. Okay. So, and imagine that in general, we have very large quantities that are burned. So we can have very large amount of CO2 production, which is a bad thing. And we should try to reduce this. We will see how. Okay. Now, of course, for each type of oil, for each type of hydrocarbons given in a certain oil type, you can, they will give us, just you should know the chemical formula of your hydrocarbon, and then you will be able to write your chemical reaction. So same concept always. Okay, let us try it again here in this chemical reaction. So I have C5H12, and I should add O2 to have CO2 and H2O. First step, I say in C5H12, how many atoms of C do I have? I have 5 atoms of C. So if I have, let's say, 1 molecule of C5H12, it will contain 5 atoms of C. So it will produce 5 molecules of CO2 because C is present only in my hydrocarbon and in CO2. And due to conservation of mass, if I have C5 here, I will have also here 5C. So it's 5 CO2. Now, second, I move to H. So for H, I have here 12 H. So here also I should have 12. And since I have H2O, so I should have 6, because 6 times 2 will give me 12. And finally, I can determine the coefficient of O2, because for oxygen, I have oxygen in the 2 products. So here already I have the coefficient 6, so it's 6O. And here it's plus 5 times 2, so it's 16. So I have 16O. This is why I need 8O2, okay, because 8 times 2 will give me 16. In this way, I determine the coefficients of my chemical reaction. Once I determine the coefficients of my chemical reaction, I can say now, let's say, if I have 1 kilomole of C5H12, for which the molar mass is 5 times 12 plus 12, which will give me 72 kilogram, I will have the production of 5 kilomole of CO2, and 5 kilomole of CO2 is 5 times 44. 5 times 44 will give me 220 kilograms. Okay. So here for each type of hydrocarbon, I can determine the amount of CO2 that is released. So now if we want to do a small, simple calculation, if I have a 500 megawatt coal-fired power that consumes 250 tons of coal per hour, okay? And for each, let's say, for each for each 1 ton of coal, I am producing a corresponding amount of 44 over 12 CO2. Okay, why? Because if you have C, let's say if you have a certain amount of C, the 1 kilomole of C corresponds to 12 kilograms. Okay, 1 kilomole of C burning coal C will lead to 1 kilomole of CO2, and 1 kilomole of CO2 corresponds to a molar mass of 44 kilograms. This means that if I burn 12 kilograms of coal, I will produce 44 kilograms of CO2. Therefore, if I have in a coal-fired power plant, I have 250 tons of coal per hour. This will lead to 250 times 44 over 12, which is equal to 917 tons of CO2 per hour. So you imagine the amount of CO2 that is produced by this power plant system, which is really harmful for the environment. So coal, which is fine powder, when mixed with O2, will do a combustion to create a huge fireball, acting as a black body transporting heat through radiation that is incident on the boiler tubes lining the walls of the combustion chamber. So here you have when you produce energy, okay, you can do your combustion inside a combustion chamber, and the heat of combustion can be transported through the radiation mechanism. Okay, now if you remember in chapter 2 we have seen that heat, especially for fire, the main mode of heat transfer is by radiation when we do when we have a fire. Okay, of course, also if we just put a thing directly on the fire, we can have it by conduction. Okay, and also if we have moving air close to the fire, we can have heat transfer by convection, but the dominant mode of heating by fire is radiation. Okay, because it will we will have exchange of heat through difference of temperatures between surfaces. So we have, due to this high amount of CO2 production, we have large deposits of slag over a long period of operation, okay, which will require a continuous maintenance, continuous maintenance for the plant. Okay. Now, a combustion of coal is complex and it involves first the evaporation of water trapped inside the coal, which will use some of the energy content of the fuel, because sometimes we have humidity, okay, humidity in coal. So when we do the combustion, part of the energy will be lost in order to evaporate water. And in general, sometimes when doing the calculation of heat of combustion, we take into consideration this heat loss, okay? Because what we want is the final used energy, not the total one. What we care about is the useful energy after evaporation of water. And due to combustion of coal, we have production of combustible gases that can be harmful to the environment. And of course, if we have, for example, incomplete combustion, we can have formation of CO and SO2. And CO is it's very harmful for environment. Okay, this is why we try to, in general, to give sufficient amount of O2 to minimize the production of CO. And for SO2, it it is an acid rain contributor, and it is fixed by using scrubber prior or post coil combustion or gasification of coil with air and steam. So we have several strategies that can be used to reduce the amount of the production of these pollutants. Now, controlling the emission of sulfur dioxide and nitrous oxides from fossil fuels power station is also a very important issue, since it's a major contributor to acid rain. So this can be done using several techniques. First, we can do it by removing the sulfur prior to combustion by coal scrubbing and oil desulfurization. Second, we can do gasification of coal under pressure with air and steam to form gases which can be burned to produce electricity. And another strategy is flue gas desulfurization, in which the waste gases are scrubbed with a chemical absorbent as limestone. And but as you can see, these are complex procedures. This is why these processes typically add about 10% to the overall cost of electricity. Okay, and this is why sometimes we say that due to the high cost we don't do them, but currently, due to the very harmful effect on the environment, we are doing these strategies to reduce the production of this harmful gas. Okay. Now, other strategies to reduce the harmful effect of combustion are carbon capture and storage. And this is one of the topics of your projects. I don't know if someone choose this topic, but it's a really important topic and it is currently under research. So International Energy Agency forecasts a 25% increase in global emission of CO2 from energy-related sources between 2008 and 2035. Therefore, to offset for this increase and its impact on global temperature rise, we have several carbon capture and storage strategies that are being developed. So first, we have the technique of carbon capture and use, which is also used in the production of fuels, plastics, building materials, chemical, and beverage industry. And it consists on capturing carbon of CO2 before being emitted to the environment. So, and we have enormous technical, political, and economical and environmental challenges that are preventing the development of these strategies on global scale. So, especially in countries under development, because these strategies are have a high cost and need high development in technology. So, mainly we are using the strategies in developed countries. Now, in principle, we could capture CO2 from power stations and industrial plants that burn fossil fuels directly at the source. This will reduce the efficiency by 10% of a given plant, since energy penalty is needed to do the job. Capture, transmission, and storage will add nearly a certain cost, okay, to the use of gas, and this is why we are predicting that this cost can increase with time, and this will cause the increase of use of coal plants. This is why what we are doing currently is that we are trying to go to renewable strategies, because in renewable strategies we will have no production of these gases, and therefore we will use a free energy without having harmful effect to the environment. Okay, so
Doctor,
in this, yes,
from a legal side, is that they want to push for renewable energy truly, can't they make مثلا هيدا الكوست legally على الكربون plants مثلا على الفوسل?
yes, of course. Look, in countries under development, sometimes it's very, like our country here, you can say I will put legal strategies, but in the real case, applications is different. Okay, you should reach a very high level of knowledge for the population, and of course the country should be, the government in the country should be very powerful to be able to impose these legal issues. Okay, so in developed countries this is working, but in countries under development it is still difficult to impose these issues. Okay.
Yes, thank you.
Okay, so if you want, this chapter introduced for us the problems we are facing using fossil fuels. And from this chapter, we see that there is a huge need to shift to renewable strategies. This is why in the future chapters, we will go over different renewable strategies used currently, which are mainly hydropower, wind power, and solar energy. Okay. So this is chapter 4. It's a small chapter. So we can today also start to do chapter 5. So in chapter 5, we will introduce hydropower, which is production of power using, as its name, using water motion. Okay, so as we said, one of the renewable energies that can be used is hydropower, and as its name indicates, it's the production of power using water. Okay, how can I produce power using water? Do you remember from the introduction? What do we do?
We use the turbines.
Turbines.
Exactly. We can use just motion of water to drive a turbine. As simple as that. Okay. Now we can rely, if you want, sometimes we use a potential energy of water, which will be transformed into kinetic energy, because when water will fall from a high level, okay, the potential energy will be transformed in kinetic energy, and after the kinetic energy, when reaching the blades of turbines, will be transformed into mechanical energy of rotation that will drive the alternator that will produce the electricity. As simple as that. Okay. But now, before just starting with hydropower, I will just go over some fluids concepts. I will not go deep in details, but just I want you to know some concepts in fluids, which will help you to understand how energy will be converted from one form to the other. So first, we have what is called the no-slip condition. What do we mean by the no-slip condition? You have a fluid that is directly into contact with a solid, will stick to the surface due to viscous effect. Okay, so we don't have slipping between the fluid and the surface. In this case, we say that we have the no-slip condition. So for example, if you have a flow of fluid over a plate, over a flat plate, at the level of contact between the fluid and the plate, since the plate is fixed, then you will impose a velocity of 0 on your fluid. And far from your surface, the velocity is uniform, equal to v. So what will happen here, we say due to viscosity of the fluid, the velocity will change in a gradual way from 0 at the surface until reaching back the value of the uniform velocity very far from the surface. Okay, so this is called the no-slip condition. And due to the no-slip condition, we have what we call the formation of boundary layer. Okay, what is boundary layer? It is the zone in which, if you want, it's the transition zone in which we move from 0 velocity to uniform velocity. So here, maybe it will be clearer for you in this figure. You can see that if I have a fluid over a rigid surface, I have, due to this effect, I have the formation of the boundary layer. So inside this boundary layer, I will have transition of velocity from 0 until it will increase from 0 until reaching the stream velocity at the end. Okay. Now, why we are talking about boundary layer? Why I want to introduce you to boundary layer? Because we will see mainly that our applications are far from boundary layer. So in our applications, we will neglect viscous effects. Viscous effects are effects that lead to smooth variation of velocity. So here you vary from 0 towards final velocity. Okay. But if I am working in this region, if I am working far from the wall, I can say that far from the wall, my velocity is uniform, no change in velocity. So this will help us into classification of fluids. So how we classify fluid in general? We classify them into viscous flows and inviscid flows. When we say viscous flows, these flows in which the frictional effects are significant. Well, what we mean by frictional effect is viscous effect. Okay. So in the example I just gave you, in the boundary layer zone, you have variation of velocity due to viscous effect. So always we say that in the boundary layer zone, we cannot neglect viscous effects. Okay. And you will have a certain profile of velocity varying from 0 to the velocity of the flow. But far from the wall, we can say that the effect of viscosity are negligible because we don't have any more variation in velocity. This is why we can say for the same fluid, we can divide it into regions. So here we can say that in the boundary layer, I cannot neglect viscous effects. While far from the boundary, I can treat my flow as inviscid. What do I mean by inviscid flow? So in many flows of practical interest, there are regions, typically regions that are not close to solid surfaces, where viscous forces are negligible compared to inertial and pressure forces. What we mean by inertial forces, okay, forces due to acceleration of the fluid. Okay, so when your fluid is in motion, you have what is called inertial force. And higher if you have an acceleration of your fluid, okay, due to a motion of your fluid, higher velocity, higher acceleration, you have higher inertial forces, which will cause, if you want, that can be dominant over viscous effect. This is why very far from the solid, you will say that I will neglect any change in velocity here because I am far from the boundary layer, and I can consider that the effect of viscosity are negligible compared to the inertial and pressure forces. Okay? Now, for fluids also, we have what we call laminar flow, turbulent flow, and transient flow. When we talk about laminar flow, it's a highly ordered fluid motion characterized by smooth layers of fluid. The flow of high viscosity fluids, such as oils at low velocities, is typically laminar. So here, when I say it's a laminar flow, it's a very smooth flow, very ordered flow. So if you observe the flow, you have particles will move along smooth lines that are called streamlines. The streamlines are lines that are tangent to the path of your particles. So here, as you can see, all your lines are parallel, very ordered. And laminar flow are characterized in general by small Reynolds number. We will see what is the definition of Reynolds number. Okay, Reynolds number is proportional to the velocity of the flow and inversely proportional to the viscosity. So more your fluid is viscous, okay, then it tends to be laminar, and more it is slow, also more it tends to be laminar. Okay, because imagine if I increase a lot the velocity, what will happen? With a lot of increase of velocity, I will start to have turbulence. So the order, I will lose my order because imagine that you are having a very high velocity. Automatically, this will cause disorder in your molecules due to turbulence effect. So we say we have a turbulent flow when our flow is highly disordered. So we have a disordered fluid motion that typically occurs at high velocities and is characterized by velocity fluctuations. So in this case, the flow of low viscosity fluids, such as air at high velocities, is typically turbulent. So always, as we said, to judge if it's laminar or turbulent, we look to the Reynolds number. The Reynolds number is defined as rho of the fluid, okay, times velocity of the fluid, v, times a certain characteristic length, we call it LC. What is the characteristic length? For example, if you have a tube, we use the diameter as characteristic length. If you have a flat plate, we use the length of the plate, etc. So it's a length that is characteristic of the geometry you are studying over the viscosity. So from this expression, you can see that higher is the velocity, higher is the Reynolds number, and higher is the viscosity, lower is the Reynolds number. This is why they tell you if the fluid is of low viscosity and if it is moving at high velocity, so it's typically turbulent flow. However, if I have a high viscous flow and moving at low velocity, as case of oil, then it's typically a laminar flow. And I have in general a zone in between. So if I am between laminar and turbulent, we call it transitional flow. So in this case, I am having a transition zone between laminar and turbulent. So it's not highly disordered and it's not perfectly ordered, so it's in between. Okay. Now, to judge in which zone I am, I calculate the Reynolds number. And based on the Reynolds number, I can decide in which zone we are. And we will see this after. Now, all we did until now is to understand one of the basic equation that is used to understand the energy conversion from one state to the other, which is Bernoulli equation. Bernoulli equation is one of the most popular fluid relations, and despite its simplicity, it has proven to be very powerful in solving engineering problems. Okay, and it is an approximate relation between pressure, velocity, and elevation. But we should pay attention for the condition to apply it. Okay, it is valid only in regions of steady, incompressible flow where no frictional forces. We don't have frictional forces, or frictional forces are negligible. So no losses, no losses. Okay. So it's equivalent, if you want, to conservation of energy that you are familiar with. You are familiar, if you have taken the dynamics course, or at school, you have taken the conservation of mechanical energy. Okay? Bernoulli equation is similar, but it's for fluids. While in general, you were applying at school conservation of mechanical energies for solids, for rigid bodies. Okay? So now, as we said, we have conditions to apply Bernoulli. One of these conditions is to have incompressible flow. So we have constant density nearly, no losses, and we are working in steady conditions. So we have a Bernoulli equation for transient conditions, but the familiar Bernoulli equation is for steady flows. Okay, and also because we don't have losses, this means that we are far from what? We are far from boundary layers, and we are far from viscous zones, because when you have viscous effects are equivalent to resistance, to friction. Okay, so to be able to apply Bernoulli, I should be far from the boundary layer. So here, for example, here if I go back to the example here, to apply Bernoulli relation, I should not be inside the boundary layer. It's wrong if I apply Bernoulli inside the boundary layer. I should be far from it in the uniform flow region. Okay, so the Bernoulli equation is typically useful in flow regions outside of boundary layers and wakes. Wakes are, if you want, circulation zones. So for example here, if you have a rigid body and you have a flow over it, okay, what will happen? When your flow will hit the body, you will have separation. You will have separation of the flow. And when you have separation of the flow, this will create what is called a wake region, where you have, if you want, it's like a zone where you don't have, the velocity of flow is very small. Okay, and beyond it you have motion of a fluid. This is why we call this zone wake zone, where we have small velocities of fluid, while far from it I have fluid motion. Okay, so now I don't want you to get into very small details here, because it's typically fluid details, but I will just, if you want, explain the general idea. The Bernoulli equation is simply the application of the second law of Newton on the fluid. So like in dynamics, you do sum of forces equal ma when you have motion. For the fluid, if you take a very small element of fluid here, and you put all forces acting on it. So if you take this element of fluid, what are the possible forces acting on it? You have, of course, the weight, you have the pressure forces, but as we said, we will neglect what? We will neglect friction. So no viscous forces, okay? This is why we should always look if our assumptions are satisfied or not, to know if we can apply Bernoulli equation or not. So always look at the conditions. Am I in a case where I can neglect viscous effect? If yes, it's fine, I apply Bernoulli. If no, then I cannot apply. And you know what? In this case, if I cannot apply Bernoulli, I go back to what? I go back to chapter 2 and 3. I apply the energy equation, because in your energy equation, you take into account all forms of energy. Because when you put work and heat, you take into account possible losses, okay? Because you can lose heat or you can lose work, for example. So in this case, the general, if I don't have application of Bernoulli, I can go to the general rule, which is the energy equation, which we used, which is the first law of thermodynamics. So the first law of thermodynamics is always applicable, while Bernoulli equation is restricted to cases where we can neglect losses, we can neglect viscous effects. Okay?
دكتور وفي
Occupation of heat.
كل flow turbulent
نعم.
الفلو في يكون turbulent نحن عم نستعمل Bernoulli equation.
In general, we use Bernoulli for laminar flows. Okay, because you will apply Bernoulli on a streamline, and if you don't have an ordered streamline, you cannot follow it. Okay, so Bernoulli in general is applied for laminar flows because you have smooth, you have a streamline, and the streamline is ordered, so you can follow it. Can follow it with time. Okay.
بس نحن قلنا انه برنولي بنستعملها when it's not viscous.
Yes.
بس if it's not viscous كأنه viscosity it tends to go to zero, Reynolds number would be very high.
Look, you say انتبه على شغله. Non-viscous مش يعني مش laminar, because laminar flow can be ordered. يعني if you want to, if I have a boundary layer far from the region, I still can have a laminar flow, but it will be I will not have variation in velocity inside. Okay, so I can reach condition of the inertia effect becomes yes, I see what you mean. You mean that Reynolds is inertia over viscous, and you say if I neglect viscous, this means that inertia is dominant and I can have turbulent flow. This is what you mean, yes?
Yes, exactly. I know viscosity tends to go to zero.
Yes, I see. Okay, it's true from this point of view. It's true, but sometimes even if you want let's say mainly in the zones here very close to the surface, you will have Reynolds number very, very small. Okay, but you still can have a Reynolds number that is in the laminar range, but it's relatively high. If you are a mechanical engineer, you know that nearly, let's say for certain application, we take Reynolds to be turbulent above 2300. Okay. So if I am in a zone where I am close to 2300, even if I am in laminar zone, I still have the inertia that is dominant over viscous effects. So I still can apply Bernoulli equation. Okay.
Okay.
Now, why I was saying that in general we apply it in not very turbulent zones, because you should apply it on a streamline. And when you have a turbulent flow, it's you cannot easily know your streamline. So if you look at your figure here, what is streamline? Definition of streamline: if you take a picture of your flow, you should see the velocity vectors. Okay, so here if you take a picture, you can see your velocity vectors, let's say like this. So your streamlines are very clear. Your streamline is just, for example, here it's a straight line. The streamline is always defined as line tangent to the velocity vectors. So if you have a laminar flow, your streamlines are smooth, while if you have a turbulent flow, they are not smooth. Okay, and it's difficult to identify them. This is why what I am saying here is that I should have a clear streamline to follow in case I am applying Bernoulli equation. That's the whole idea. Okay. Okay. Now let us continue. So